This is Lecture 1 of Module 5 from the book Problem Solving Guide for Mechanics and Thermodynamics. This lecture is on the elastic force. Here we are going to be dealing with elastic forces, the force exerted by a stretched spring or an elastic cord. It is assumed that the force is directly proportional to the distance the spring or the cord is stretched. Or in the case of a spring, it can be compressed and still have stored energy. The equation is F equals kx. The force is the stiffness times the distance from equilibrium. Well, there's a minus sign in there, but the minus sign only tells you that if you stretch a cord, the force the cord exerts is back in the negative direction, in the opposite direction. But we don't need math to tell us which way the force is. We need an equation to tell us how big the force is. So the force is kx. We can write the absolute value of x, okay? The magnitude of the force is k times x. That's what we want that equation for. K is how stiff the cord is. It's called the spring constant, the stiffness. It's simply how much force it takes to stretch a cord a certain distance. So a typical spring constant, 20 pounds per inch. If a 100-pound weight is suspended from this spring, it stretches a distance of 5 inches. If a 10-pound weight is suspended from this spring, it stretches half an inch. 100 pounds per inch, an inch for every 20 pounds. That's the stiffness. It'll stretch 5 inches if you hang a 100-pound weight from it. Another example of a K is 10 newtons per centimeter. If a 1 kilogram mass was suspended from this spring, it would stretch a distance of 1 centimeter. The force on a 1 kilogram mass in the gravitational field of the Earth is 10 newtons. 10 newtons every centimeter, it stretches 1 centimeter. The springs on a car that absorb the shocks, the suspension, right there, it's about 500 pounds per inch, right? That's a stiff spring. In physics lab, we have springs like this. Once again, to get the stiffness, we look at the force it takes to stretch it a distance. If we look at the scale here, it goes from 0 to 50 newtons in a distance of about 10 centimeters. 50 newtons in 10 centimeters, the stiffness is 5 newtons each centimeter. K is 5 newtons per centimeter. Again, when solving problems, that x in the F equals kx is the distance from equilibrium, not its total length. So the bungee cord is 60 meters long. Okay, that's the relaxed length. That does not belong in the x. The x is how far it's stretched from 60 meters. There's no energy stored if it's not stretched. So the reason why we dedicated an entire lecture to this is that the force is not constant. All the other forces we've dealt with so far are constant, right? Gravity, it's mg. Friction, tension, applied forces, normal forces, they're all constant. The elastic force increases as the stretch increases. This is going to introduce complications when trying to determine the work it takes to stretch a spring and how much energy is stored in the spring once it's stretched. The concept of work will be investigated in the second lecture, and we're going to talk about energy in the third lecture. Here we're going to assume that the product of the magnitude of the force and the distance moved in the direction of the force is the work. So as a simple example of this, consider a 1 kilogram mass falling 10 meters downward in a gravitational field. The force of gravity on that 1 kilogram mass is 10 newtons. It moves 10 centimeters in the direction of the gravitational force, straight down. The work done by gravity is 100 newton meters. A 10 newton force exerted over a distance of 10 meters. We call this a joule, which is a newton meter. It's a unit of energy. We can write the same equation for the work done to stretch a spring. The problem is that force is not constant. Gravity is easy because the force of gravity is always 10 newtons on that mass. As we pull out the spring, the force gets harder, bigger and bigger and bigger. It's easy in the beginning. We could get an estimate by dividing the stretch into smaller increments and assuming the force is constant over the stretch, which it's not. That's why it's an estimate. So if we wanted to determine an estimate of the work done to stretch a spring 4 centimeters that has a stiffness of 5 newtons every centimeter, we can divide it up into 4 increments. from 0 to 1 centimeter, from 1 centimeter to 2 centimeters, from 2 to 3, and then from 3 to 4. So the force is 0 at the beginning of the stretch, so we're going to get 0 for the work done because we're assuming the force is constant throughout that stretch. So from 0 to 1, we're going to get the wrong answer. We're going to get 0. From 1 to 2, the force it exerts when it stretches 1 centimeter is 5 newtons. 5 newtons every centimeter. That's the spring constant. And we're going to assume it's 5 newtons the whole time, even though it's increasing. So the work done to go from 1 to 2 is 5 newton centimeters. Once you're at 2, the force the spring exerts is 10 newtons. To stretch it from 2 to 3 centimeters, 1 more centimeter, assuming the force is constant the whole time, requires 10 newton centimeters of work. Finally, when going from 3 to 4, we're going to assume that the force is constant, 15 newtons over the whole centimeter. That's 15 newton centimeters of work from 3 centimeters to 4 centimeters. The total is 30 newton centimeters, but we know this is too low because the force is increasing during each pull. If you wanted a better estimate, we could divide up that 4 centimeter distance into 40 segments of 1 millimeter and assume the force is constant over each 1 millimeter pull. And we're going to get a much better estimate. But if we wanted the exact answer, we would have to divide it into an infinite number of distances and recalculate the force at every single one of those distances. And we can do that. We can do that with calculus. The amount of work done when stretching the spring by an infinitesimal amount dx is dw, and dw is f dx. Now, if you're paying attention and thinking, you might say, wait a minute. Just because you have the force is still getting bigger, how can you put an f here? What f is this? Is this at the beginning of the stretch or the end of the stretch? Isn't the f changing during the stretch? And the answer is no, it's not. Because the variable dx is not a distance. It's an idea. If you plug in a distance, you're going to get the wrong answer. The smaller the distance is, the better your answer is going to be, but it's still going to be wrong. If you put dx in there, then it's exact. It's infinitesimal. It doesn't have a value. You can't substitute any length in for dx. If you do, you're going to get the wrong answer. This makes the work done by the force dw. That's infinitesimal as well, because the distance you pull it is infinitesimal. So how many dx's do you think we need if it's infinitesimal? We need a lot of them. We need infinity. In calculus, we can sum up an infinite number of infinitely small things and get an answer. Believe it or not, this is the concept of calculus. And this is what makes calculus so challenging to understand. I'm not talking about being trained like a seal to do an integral or a derivative by following a set of rules. I'm talking about understanding what dx means. That's the hard part. In fact, when Newton invented calculus and the infinitesimal, he was criticized. Now, what are these evanescent increments? They are neither finite quantities, nor quantities that are infinitely small, nor not yet nothing. May we call them the ghosts of departed quantities. So what possible use could there be for a variable that was almost zero and could not be assigned a value? That's a good question. So now let's do this sum. dw equals f dx. To indicate that we're going to sum up both sides, we use an elongated capital letter S, like this. That's an integral sign. On the left-hand side, we have the sum of all the infinitesimal works. If we add up all the little works it takes to stretch that spring, we're going to get the total work. That's W. That's pretty straightforward. The right-hand side is harder to calculate because F is not constant. So let's put in the expression. It's F is Kx. So now we're going to sum up the Kx dx's. So let's write out the first few terms just to make sure we know what the heck we're doing. So the integral of Kx dx is the sum of all the Kx dx's from 1 to infinity. There's an infinite number of them. So we're going to write out that sum. That's the first one. That's the first stretch. That's the first force. That's the first distance we stretched it. That's the second force. That's the second distance we stretched it. Kx3 is the third force, and that's the distance we stretch it. It's very similar to the breaking it up into 4 1-centimeter increments, but now we have an infinite number of increments. Infinite number. Every term has a k and a dx in it. The dx's are all the same. dx1, dx2, dx3, that's just a little teeny distance that we stretched it. We can factor these out. So now we have all these x's, and these x's are the distance at the start of the stretch. And how many of those do we have? Infinite. It's a big sum. We're summing up all of them from 1 to infinity. It's a big number. So those are the distances at the beginning of every infinitesimal stretch. The first stretch is from 0 to dx. The second stretch is from dx to 2dx. The third stretch is from 2dx to 3dx, all the way out. Keep going, etc. So that's the first x dx, the second x is 2dx, the third x is 3dx, and we can factor out a dx from that. And we get k dx squared plus the sum of all the integers. What's the sum of all the integers from 1 to infinity? Nobody knows. It's big. But we do know the sum of a very large number from 1 to a very large number n. It's n squared over 2. What's the average of a very large number of numbers? All the integers from 1 to n. It's n over 2. It's the one in the middle. How many of those numbers do we have? We have n of them. So the sum is n times the middle one, n squared over 2, n over 2, which is n squared over 2. So that's the sum of all the integers from 1 to a very large number n, and we can substitute that into our expression. So this is the sum of all the integers from 1 to n, and those are the terms we factored out, and we can actually get an answer for this. We can rearrange it. So let's pull out the 1/2, put it in front, and group the n's and the dx's. So we have 1/2 k n dx, quantity squared. But what is n dx? We divided some distance, this total stretch, into an infinite number of increments, n, and each increment was dx. So n dx must be the total stretch. Now we can write the integral of kx dx is 1/2 kx squared. X is the distance of the total distance of the stretch, x max. Since this is the work done to stretch it a distance x, it's also the elastic potential energy stored when it's stretched a distance x. So elastic potential energy, which we'll deal with in Module 3, is 1/2 kx squared. Not Module 3, Lecture 3 of this module. So we can now use this expression to get an exact answer for stretching a spring of stiffness 5 newtons every centimeter, a distance of 4 centimeters, and we get 40 newton centimeters. And we estimated 30 newton centimeters, and we knew that was too low, so that's consistent. If you have taken a calculus class, you might already know that when you integrate x dx, you get 1/2 x squared, which is what we just did. Hopefully now you understand why we actually did the sum. In the next lecture, we're going to derive the work energy theorem and apply it to solve some problems, for example, a bungee jumper. What's going on there? That's Lecture 1.